Okay, let's try this out. Game of roulette. We have 38 slots, 0, 0, 0, and then every integer from 1 to 36. Ball falls into the slots with that matches the number you selected. You win $35. Otherwise, you lose $1. Okay, let's see here. You're only picking one number. So you should only be winning if these are equally likely. 1 out of 38 times, they want us to round to 4 places. So 0.0263, 0263, and should just be a matter of 1 minus that answer. Let's double check that. 1 minus 0.0263. Okay. 37 over 38 when rounding to 4 places would round to the same place. 0.9737. Being in the standard deviation. Okay. This would be, the mean would be 35 times the 1 over 38. So 35 38ths plus the -1 score. So I'm taking score times probability of that score. Can't get to my negative sign here, so I'm going to work around that. That was happening 37 out of 38 times. Now, they may want us to have used the rounded stuff, but let's see what happens. Round to the nearest penny. So that would round down. I would expect on average to lose 5 cents. The standard deviation. All right, let's see here. I'm going to do this in a table. So we take our scores. The probabilities. And give me a moment. Got to remember how to do standard deviation for the discrete variables. All right, I have to admit that I temporarily forgot, although I think I was close to the first formula with what I had in my mind. All right, so we found a mean of negative 0.05. So let's take those scores, x's, and square them. Scores minus the mean. Now we're subtracting a negative 0.05, which is going to be the same as adding 0.05. So add 0.05 positive to each x, square it, and multiply by the probability. So I went to the top of the column and pressed enter. Score in list 1 minus a negative 0.05. Again, I can't get to my negative. It's going to have the same effect as adding 0.05 positive. I could have done this all at once, but I'm going to square those and multiply by the probability. So going to the top of that column, tell it to take what's in list 3 and square it. Put parentheses around this just in case. Square it, and then multiply by the probability from list 2. We then want the sum. Notice what we're seeing written here is not as detailed as what's showing at the very bottom. So I'm going to let the calculator find the sum of list 4. And then I still need to take the square root of that. Oh, don't want to do that. Let's get to the home screen. Second and stat. Math submenu. Sum of list 4. Take the square root of that answer. And I said to the nearest penny, so to the nearest hundredth, that would go to 5.76. See how I did there. Okay. Suppose you play the game 90 times, i.e. we've got a sample size little n of 90. Regardless of, in fact, that distribution is skewed. -1, there's only 2 scores, showing up a lot more often with a score of losing the $1. So this is skewed left. But we have a sample size of 90, which is greater than or equal to 30. So approximately normal for the sampling distribution of X bar, not the population. The mean is going to be the same as for the population. Then I'm going to divide by square root of 90. Take what I had for the standard deviation for a single game. Divide by square root of 90. Notice how I'm using the most exact version the calculator could give me instead of the rounded, just in case. To the nearest penny, that would be 0.61. See if they agree with that. Okay. So what is the probability of being ahead after the 90 games? So the probability of X bar being greater than 0, that you have some amount of profit instead of a loss. Okay. So since this is -T technology, instead of using z-scores in the table, X bar greater than 0, our shadings to the right. Start with 0 as a finite lower bound and 10 to the 99 as an infinite upper bound. Mean of -0.05. And standard deviation. I'm going to use my previous answer instead of the rounded version, and let's see what happens. Okay, can't get to it. 0.61 then. Oops. Back. Figure that out. 0.61. Hopefully it'll be okay to use the rounded version. Not even 50% of the time. 0.5. It's less than that. Not by much though. Rounded to 4 places. 0.4673. There's one more 3 after the 3 I'm talking about, and that would round it down. Again, 0.4673. So what if we went up to 270 games? Okay. Well, sigma was originally 5.76. And now, talking about n being 270. Let's look at n again. 5.76. 5.76. Just leave everything else the same. Now divide by the square roots of 270. Checking that before I press enter. Yep, play 270 times. It's gone down. That 8's going to round the 2 up, 0.4433. Yep. So the more you play, the more likely you are to, on average, be losing. I think we'll see that showing up even more when we replace the 270 with the 900 in this parts. I was down to 0.3973 when we play the game 900 times. So the probability of being ahead, that you're making a profit, that X bar is greater than 0. It's decreasing as the number of games increases. Okay, that should be everything that I've got for now. All right, yes it is. So Professor Sargent signing off. Stay safe and healthy, and hopefully I'll see you in another video.